When considering the overall requirements for the software that we want to build, we must also consider its security requirements. Normal software requirements are about what the software should do. Security requirements outline the security expectations of the software's operation, and these come in two flavors. First, there are the security-related goals, or policies. For example, a policy for our online bank application might be that one user's bank account balance should be private. That is, no other user should be able to figure out what it is without proper authorization. Second, we may have requirements concerning the mechanisms we use to enforce security. For example, we may require that for password-based authentication, passwords must be strong, and the database storing those passwords must not be accessible to any program other than the authenticating login program. Now let's dig a little deeper and explore different sorts of policies and mechanisms a designer might employ. There are three classic types of policy: confidentiality policies, integrity policies, and availability policies. Confidentiality policies are sometimes further broken down into privacy and anonymity requirements. Required security mechanisms often address three sorts of activities: authentication, authorization, and auditability. Let's look at each of these elements more closely.
First, we'll consider the three kinds of security policy, beginning with privacy and confidentiality. Privacy and confidentiality are ensured when sensitive information is not leaked to unauthorized parties. We typically refer to this property as privacy for individuals and confidentiality for data. Sometimes we also refer to it as secrecy. As an example, for our online bank, the bank account status, which includes the bank account balance, should only be known to the account owner and not to any other parties. A violation of privacy or confidentiality could occur directly or could occur via a side channel. For example, it might be possible to manipulate the system to directly display Bob's bank account balance to Alice and thereby violate the policy. But it might also be possible to learn that Bob has an account at the bank because there is a shorter delay on login failure. That is, a poorly designed login system might take a long time to go through the database to find whether or not a user has an account. On the other hand, if the user does have an account, the returned login failure may occur more quickly. Another sort of confidentiality policy is anonymity. This is a specific kind of privacy. As an example, we could say that non-account holders should be able to browse the bank informational site without being tracked and having their identity compromised by the bank or advertisers that the bank works with. In this case, the adversary is not users outside the banking system itself, but instead the bank and maybe third-party advertisers. In the other examples, we considered the account holders or malicious third parties as the adversaries. The next kind of security policy that we'll consider is an integrity policy. The idea here is that sensitive information should not be damaged by computations acting on behalf of unauthorized parties. For example, only the account owner can authorize withdrawals from her account. If some other party were able to effect an account withdrawal, that would violate the integrity of the bank account balance. Once again, violations of integrity can be direct or indirect. For example, we may be able to specifically withdraw from the account because the account system does not properly authorize such actions, or there may be a way of confusing the system into doing it, for example, by using a cross-site request forgery. The third sort of security policy we'll consider is availability. In this case, availability means that the system is responsive to requests made to it. For example, we may want a user to always be able to access her account balance for queries and withdrawals. We do not, on the other hand, want a denial of service to be able to take place. In this case, an attacker is able to overwhelm a site with useless requests and thereby prevent the site from servicing the reasonable ones. Another way of having a denial of service attack is simply to cut off access via the network to the site. Once we've defined the security policies we have in mind for an application, we have to think about how we're going to enforce those policies. Leslie Lamport defined the gold standard as the three sorts of mechanisms often provided by a system to perform this sort of enforcement. These mechanisms include authentication, authorization, and audit. And of course, gold comes from the first two letters of each of these actions, AU, from the periodic table. The gold standard is both a requirement and a kind of design. In particular, the sorts of policies that you are considering may determine what sort of authorization mechanism you need to use. For example, if you're using user versus user policies like in our online banking system, we need to have an authentication and authorization mechanism that distinguishes the actions of different users. The kinds of users that we consider may determine how we authenticate them. Okay, let's consider the first element of the gold standard, which is authentication. The goal of authentication is to determine the subject of a particular security policy. In particular, many policies require a notion of identity. In order to authorize a particular action, we need to know who is performing that action. By who, we also mean a principal. That is, it could be a human being, or it could be some service or computer program. Either way, we need to identify that actor and determine whether the proposed action is consonant with our policy. So the question that authentication tries to answer is the user who he says he is? That is, a principal that claims to be a particular identity. Can we tell whether or not that claim is true? We might do this in several ways. First of all, we might try to see whether the claimed user knows something that only the real user would know. This is the theory behind passwords. Only the real user should know his or her password, and therefore if the password is entered correctly, we must be dealing with the real user. Another approach is to base it on something that the user is, like a biometric. So for a human user, we might check a retinal scan or a fingerprint. Another idea is to base authentication on something the user has, like a smartphone. We might assume that a particular smartphone phone number is only in the possession of a particular user, and therefore communication via that phone will be to that user. Authentication mechanisms that employ more than one of these factors are called multi-factor authentication mechanisms, or MFAs. As a common example, a bank may employ passwords as a first factor and then send a text of a special code to a user's smartphone, asking the user to enter that code before authentication is complete. The next element of the gold standard is authorization. Authorization defines when a principal may perform a particular action. For example, Bob is authorized to access his own account, but he is not authorized to access Alice's account. There are a wide variety of security policies that involve some sort of authorization. For example, the policy we just saw is a user-based access control policy. That is, access is defined in terms of the users performing particular actions, like Alice or Bob. Access control policies could also be role-based. For example, a bank teller or a bank manager may be allowed to perform certain things, and different individuals may at different times fulfill that role. Policies could even be originator-based. For example, Bob could originate a policy that allows Alice to withdraw a fixed amount of money from his account. The final element of the gold standard is audit. The idea here is to retain enough information to be able to determine the circumstances of a breach or misbehavior, or to establish that a breach or misbehavior did not in fact occur. Such information is often stored in log files. In order to be trustworthy, we must protect these files from tampering. As an example, every account-related action may be logged locally and then mirrored at a separate site to avoid tampering. These logs could be used, for example, to confirm or refute a claim that Bob might make that a withdrawal took place from his account.
How should you determine what your security requirements are? There could be many processes that you could employ. First, forces external to your particular project may come into play. There may be laws or regulations governing applications of the kind that you are setting out to write. For example, if you are writing an online health record database for use in the US, you must consider the privacy requirements mandated by HIPAA, the Health Insurance Portability and Accountability Act. Or if you're writing a financial management application, you may need to consider the implications of Sarbanes-Oxley, also known as SOX. You may also be encouraged to implement security requirements in line with your organization's values. For example, if you work at a consumer advocacy organization, you might have a strong inclination to protect user privacy. Security policy requirements might also arise from the exercise of threat modeling and architectural risk analysis. After considering the likely adversaries and their goals and capabilities, you might identify resources that you should protect. You might also draw insight from prior attacks that you have observed or experienced to know more about what resources are security relevant and how they might be compromised, and thereby define policies or mechanisms aimed at thwarting potential attacks. A particularly fruitful activity can be the design of abuse cases. In traditional software engineering processes, use cases are stories describing how software or software features can be used. As such, they illustrate functional requirements. Abuse cases, on the other hand, illustrate security requirements. In particular, they identify things that a software system should not do. Considering our online bank application once again, an example use case might be that the system allows bank managers to modify an account's interest rate. An abuse case would be a user who is able to masquerade as the manager and thereby change the interest rate on his own account. What process might you use to come up with abuse cases? One approach is to start with likely scenarios and patterns from known attacks, and then think of cases in which an adversary can break a security requirement. An adversary's power is determined by the threat model, and the violation of the requirement could be due to a failure of an assumed security mechanism. For example, suppose we are assuming a co-located attacker. Then an abuse case might be that the attacker steals the password file, which is within his capabilities as being co-located, and thereby learns all of the passwords. He might be able to do this because the password file is unencrypted. Another abuse case might be a snooping attacker that is able to capture a user's message and then replay it. If the banking application cannot tell replayed messages from the originals, then the replay might have negative consequences. For example, it could affect a repeated transfer of funds from an account. Such replayed messages might be prevented by including a nonce or other unique identifier in the message.